All right, this is a doozy of a calc problem. We're going to do find the upper and lower sums for a region bounded by the graph of, here's f at x equals negative x squared plus 8, and the x-axis, and from where x is 0, clear up to where x is 2. And so we're going to use summation notation to do this. But before we do this, we need to take a look at what the graph looks like and what we're talking about. So here's my function, f at x equals negative x squared plus 8. I just plugged it in here. And we want this shaded region, the area of this shaded region from 0 to 2 on the x-axis up to the function. And so there's a couple ways you can do this. We're going to start out with the basics of summation notation, and we're just going to slice it into rectangles. And so if you take that and we slice it into 3 rectangles, we'd get and go up to the function on the left slices here on the left. So my left side hits the function, and just continue the rectangle on out. You'd get a approximate area of 14.5. Now, if you wanted to take a look at it from the right slices, so now it's the same thing, but it's a little bit of an underestimate because we're going to use these right lines for the height of my rectangle. And so when you come back across, looking like a bar chart here, we've got that area from 0 to 2, and it's slightly higher. It's 11 point, or slightly smaller. It's 11.582. And if you look, so we know our area is somewhere between these. What's cool about this thing is you can increase now. So there's 4 rectangles, 5 rectangles, 6 rectangles, and so this is, now we're up to 31, 46, and you notice these two numbers are starting to zero in on this area between the curve. So the area down here, and you can, if you zoom in, you could see still we've got a little over and underestimates there, and we just keep going. Keep going. You could, and we're going to take this out as big as we can. The biggest the computer can do is 500, and your left slices are up to 13.341. Your right slices 13.325. So we're kind of zeroing in somewhere around 13.3 if we went clear up to 500 rectangles. But let's bring this back down to 3. There's 6. Be quicker, just type it in. So if we type that into 3, there's my upper and lower bounds, or my left slices and right slices. And so let's take a look at this with summation notation and see if we can prove our answer is 13.3 repeating. So we need a little bit of background first. And so I've just pulled up an image of those left slices with the area and just 3 rectangles. And so what you do is we're going to find out the size of these links in the bottom, because we want them to be exactly the same. And so what we do is we'll call that the change in x. And all you do to find those links is you take your upper bound, which is 2, minus your lower bound, and divide it by however many we want. So like in this case, it'd be 2 minus 0 divided by 3. And where n stands for the number of rectangles we want. So n equals number of rectangles. A stands for lower bound, and B stands for upper bound. And so that gives us that change in those rectangles. So that's the first thing we'll need to set this thing up. Now, the other thing we need is the height of the rectangles. So if this is the left slices, we want these lengths here, this length, and this length. So those there. And so if we generalize that, that formula, and I'm going to use this notation where it's just a lowercase m sub I, and I standing for the rectangle we're on, so 1, 2, 3 for I, and the lowercase m is going to represent that height. And so to get that, it would be your lower limit plus 1 minus, or I minus 1 times delta x times that change. So this is going to stand for, yeah, what we're going to plug into that formula. And I'll show you that next. All right, so we're going to take that m sub I and plug it into the function f at x. So we're going to find this f of m sub I. And so that's what all of these will be here. This is that f of m sub I. That's hard to read. And these all down here on the bottom, just as a recap, are your delta x's. We could throw numbers in, and use the exact 3 rectangles. But let's go ahead and generalize this for the whole thing. So the next step we need is to add these rectangles up. We've got our width of our rectangle, we've got our height of our rectangle, and we've got, in this case, 3 rectangles, but we can increase it to as many as we want. We're going to keep this n, leave that alone, so we can have as many rectangles as we want to make in this left slice function. So the formula for the left sum, there's the summation notation. We're going to start at 1, and we're going to go to n, and it would be f of that m sub I times delta x. So it's the sum. So here is your height of your rectangles. Here is the base of your rectangles, or the width. And so we're going to just plug this into this formula in a general rule. So that we already know that delta x, the formula for that was b minus a divided by n. So we'll generalize that. So that would be 2 minus 0 divided by n, which would just end up with 2 over n. So anywhere there's a delta x, we can put in 2 over n. And then we had that formula up above, m sub I equals a plus I minus 1 times delta x. Well, if you plug in all your a's and your delta x's, this m sub I would be 0 plus I minus 1 times delta x, which is 2 over n. And if you simplified that, that would be I minus 1 times 2 over n. So we're going to plug this into our function. So now my summation notation for my left bound is I equals 1 to n of your function, which you might have forgotten what the function was. So let me pause. So we kind of lost track of what the function was, and it's right here, negative x squared plus 8. So we're going to plug our value into that and get rolling with this thing. So it's kind of a long process. So if you plug that into it, you would have something like this. You would have, I'm going to bracket it, it would be negative 2 over n times I minus 1, and then all of that is squared. So I better put that in there. I saw my negative out front. We're good to go there. Plus 8. And then what you'll forget to do is take it times this delta x. So if you go back up here and look, so there's the f sub mi part right there. And then we need to times it by the base of the rectangle. So we're going to times it by that delta x again, which is 2 over n. And now it's just a matter of simplifying this thing out. So I'm going to just do several steps and go over them. So I've got 2 more steps here, and I'm going to try to flip through these fast. And so I went ahead and squared everything in here. So 4 over n squared, I minus 1, and then multiply these 2 out, and you end up with I squared minus 2i plus 1. Again, I did that kind of in my head off to the side, but we'll keep on working. So in that, and again, what we do here is we distribute through. So I'll just pull that up. We distribute on through this thing. And so I'm distributing through that parenthesis. That's what I have here. And then you distribute the 2 over n back through everything. And that's what I have here. So now this one's kind of a leap because you have to know some of your properties for summation notation. And this is not a big, I'm not going to get into the details of all of this, but I'm going to just break this up now. So we've got this summation notation here, and this 8 over n cubed, that's, this thing is from I equals 1 to n. Well, n is an actual number, like it was 3 in our example, because there was 3 rectangles. Well, so n is a number and 8 is a number, so that's a constant. So we can pull that out in front of our summation notation. So this summation notation can be rewritten as negative 8 over n cubed I equals 1 to n of I squared plus, and you pull the 16 out, that's 16 over n cubed, the summation of I, minus, notice 8 over n cubed here, this is all times 1, so you could pull that out and you'd get 8 over n cubed summation of 1, and then plus the same with the 16 over n, that's also times 1, so you'd have plus 16 over n times the summation of 1. And again, all of these are from I equals 0, or I equals 1 to n, I equals 1 to n, I equals 1 to n. In all cases, all the way across. And so we're going to zero in next on simplifying these summations, because if these formulas, when you sum from 1 to n of I squared, and you sum from 1 to n of I, and you sum from 1 to n of n, all of these are going to simplify. And so I'll show you those formulas really quickly. So here's the formulas we're dealing with. And if you notice, like this one says the summation of I equals 1 to n of 1. Well, that's the one we need, where the constant is 1. Well, if you did that, and let's say you just did it to, to 3. Summation of I equals 1 to 3. Well, of 1. Well, that would be 1 plus 1 plus 1, which is 3. And so essentially it's just whatever your number is on top times whatever number this is. So the summation of 1 to n of 1 is 1 times n, or just n. So we can substitute that in place of anywhere there's a summation of 1 from I equals 1 to n. Same with I squared. So if you have I squared there, it ends up giving you this formula. And we could go through and show the proof of that, but again, I just want to get us there. We're more after the summation notation stuff. And if you multiply this thing all out, you get this function here. And again, I'm just multiplying the n through, and then distributing that polynomial by this polynomial. So just showing just basic distribution. And then the same with this one. This would also be n squared plus n if you distribute it through divided by 2. So I'm also going to plug this in anywhere there's a summation of I. So when we do these now, we're going to have negative 8 over n cubed times that 2n cubed plus 3n squared plus n all over 6. That's for this part here. And then you do the same here, plus 16 over n cubed. but now it's just the summation of I, so that was that n squared plus n divided by 2 minus 8 over n cubed. We know that the summation of 1 is just n, so I put that in place. And then the last one, plus 16 over n. And again, the summation of that is also n. The summation of 1 again. So now we're ready to distribute these all through. And so I'll do that. And so we simplify that out. The n cubes cross out, 16 and 6 crosses out. You're left with negative 8/3, n squared, and n. You go through, cross all this stuff out, simplify it. You end up with this expression here, which is just downright nasty. And we could combine some terms. I'm not going to combine them all, but I'm definitely going to combine. I'm going to definitely combine this negative 8/3 here, and I'm going to combine the 16, our two constants. You can combine all those n's in the middle, but not necessary, because I'll show you what we're going to do. All right, so I simplified these out. And again, that negative 8/3 and the 16, those ended up being 40/3. Negative 4n, positive 8 over n, that's 4 over n, and then these two on the end cross out because they're 0. And then you've got the negative 4/3 over n squared. And so now what's happening here is we can go ahead now and set the limit to this as n approaches infinity, because remember, we wanted to know we wanted as many rectangles as we could get. So let's just do an infinite many rectangles. And so if you do the limit of 40/3 as n approaches infinity of 4 over n minus 4/3 n squared, we're dividing by that, kind of important there. And so if we find that limit, notice what happens. This number becomes practically 0. This number becomes practically 0 because we're taking 4 divided by infinity in both cases, which is 0. And so we're left with 40/3. And so we've finally found our left bounds, which is 40/3, which is 13 1/3, or 13.3 repeating. So we've shown that it works on the left side, which is the much harder, more tedious side to do. So now let's look at it on the right side and make sure they come out the same. And so if we look at our right slices, we've still got kind of the same stuff. We've got our rectangles, these widths are still going to be delta x all the way across here. And to get delta x, you take your 2 minus your 0 divided by n, the number of triangles we want. I'm going to change this to a capital M sub I, but now we're dealing with the right side of this thing. So these lines right here. And so this gives you the value to plug into your function so you can find these links on the right side of the rectangle. So we found the left, now it's time to find the right and make sure that they match, and we pinch that perfect area in the middle. And so when we plug things in, then delta x is going to be the same thing. It's going to be 2 minus 0 over n, which is 2 over n. This is going to be slightly different because we're dealing with the right side, so I doesn't have to be subtracted from 1. So it's 0 plus I times 2 over n for that delta x. And so if you simplify that, we're just going to have 2I over n. So that's what we'll plug in to our function and our summation notation. Okay, so when we plug that thing in, you would have the summation of I equals 1 to n. You plug in the 2I over n into our function, which, if you remember our function, it was negative x squared. So negative 2I over n squared plus 8. And then don't forget your delta x. There's that delta x there. So if you forget that, you'll come to the end and you'll think, oh shoot, it didn't work. Well, Most of the time is because you forgot to put that delta x back in, that change in x. So when we simplify that thing out now, we go ahead and square that. That's what we have here, plus 8. You distribute the 2 over n through both of those. And so now we're looking at this summation equals 1 to n. And again, we're going to go ahead and split this thing up. I'm going to split it off to the right here. And so the summation now, you can put that negative 8 over n cubed out front. So we'd have the summation of negative 8 over n cubed times the summation from I equals 1 to n of I squared, plus, again, there would be a times 1 here. And so you could have that 16 over n times the summation of I equals 1 to n of 1. And we'll plug our formulas back in that we found previously. Again, just a recap of the formulas. Here is the I squared formula, and we'll plug this one in so we don't have to do any more distributing than we have to. We've already done it, so why do it again? And we also need this sum of 1, which is 1n, or just plain old n. We can throw n in there. So again, we've got this formula for the summation of I squared here. And so I'll go ahead and plug that in for that. And then the same with this one, the summation of 1 from 1 to n is just n. Whoops, I moved it. Whoa, crazy. So that one right there. And we'll just keep simplifying. And so again, we go through this thing and we simplify this down. We've got this distribute this 8 over n cubed through all three of these, distribute the 16, well, multiply the 16 over n times n, start crossing out. We're left with 16. That's n squared. That's n. That's 4. That's those n cubes cross out because there's 1, and that's 8/3. And so here's our new function. It's starting to shape up nicely like the other one. So we combine the 8/3 and the 16. We get 40 over 3 minus 4 over n minus 8 over n squared. And again, we want as many rectangles as we can make. So we will limit n to infinity, which n is the number of rectangles, and of this function. And you'll notice again what happens. This becomes 0. This becomes 0. Because 4 divided by an infinitely large number is 0. 8 divided by an infinitely large number, also approximately 0. And so we're left with the 40/3, which again, 13 1/3, which is 13.3 repeating. And so we've proven from both the left limit and the right limit that it works. And so just as a recap, I just wanted to show this one more time, because geometrically, this is all we're doing. As we're moving these, we're just looking at the left and the right side. So here's our left slide, and if we move that to infinity, up to 490 as high as we could go, we're getting close to the 13.3 repeating, but not exactly. And the same if you go to the right side. So again, we started here kind of with low number of rectangles. There's 1. And then we jump that number of rectangles up to infinity, and that's 13.25. And so that shows you, what's happening both geometrically and if you had to program this into a computer to do it. That's how I was taught calculus when I was a kid, was we programmed it all in. And so we didn't get to spend a lot of time with the geometric stuff, and so seeing that is pretty cool. So I hope this helps, and I'll see you next time.